I want you to imagine, for just a second, that you're sitting in the driver's seat of a brand new premium car.
Oh, yeah. You haven't even turned the key yet. Just taking it all in.
Right, exactly. Just look around the cabin. Direct your attention to that flawless interior. Notice how, like, the leather wraps around the steering wheel so perfectly, it feels like a second skin.
Mhm.
And look at the passenger seat, how the seams align without a single pucker or, weird fold anywhere. And how the fabric tension across the headrest is just completely, perfectly uniform.
Yeah, we totally take that level of perfection for granted.
We do.
I mean, it feels inevitable when you're just sitting there in the showroom. But creating that exact identical experience across tens of thousands of vehicles is
Right.
just a monumental manufacturing challenge. Creating uniformity out of highly variable materials is basically the opposite of inevitable.
That tension right there between natural materials and, manufacturing perfection, that is what we're exploring in today's deep dive.
It's a fascinating process.
It really is. We are looking at the engineering behind that precision, and we're using this incredibly detailed internal workflow data from the manufacturing experts at Velocity Plotters and Cutters.
Yeah, their breakdown is fantastic.
So our mission today is to unpack the what, the why, and the underlying step-by-step technical mechanisms behind how modern automotive interiors are manufactured with basically zero room for error. Because it turns out perfection is a highly calculated science.
Absolutely.
Okay, let's unpack this. Before we get into all the digital automation stuff, we really need to establish the stakes of the manual method, right?
Yeah,
Like
yeah.
the old way of doing things.
Right. I mean, manual cutting has historically been the standard, but it introduces just a massive amount of physical variance into the process.
Because humans aren't machines.
Exactly. When you rely on a human operator to manually cut out these intricate automotive panels, you're introducing microscopic variables with every single motion.
Mm,
You're talking about slight shifts in how the physical pattern is placed down,
right.
changes in the angle of the blade, the pressure applied to the fabric, or honestly, just basic operator fatigue at the end of an 8-hour shift.
Yeah, I was trying to visualize the mechanics of that while reading the source, and it feels akin to trying to wrap a highly complex, curved Christmas present perfectly.
Which is hard enough to do once.
Right. But imagine having to do it thousands of times in a row using thick, resistant paper. If your scissors slip even a tiny bit, you have a problem. But if the blade slips in an automotive plant, you aren't just wasting a piece of tape.
Oh, definitely not.
You're wasting incredibly expensive materials, right? Like premium leather, vinyl, specialized technical textiles, hundreds of dollars.
And it's not just the immediate waste of that one piece. That's the real kicker. In repetitive or customized production, even a single millimeter of deviation causes a massive ripple effect downstream.
Like it compounds.
Right. A slightly misshapen panel leads to misaligned seams when the sewing team gets it, which leads to severe assembly difficulties when they're actually wrapping the seat frame, and ultimately you get a rejected part.
Just from 1 millimeter.
Yeah. So to solve this, the industry shifts to digital cutting, which fundamentally changes the control mechanism from a human hand to an algorithm.
Right. And by definition, digital cutting is an automated process where a machine reads digital CAD files and executes those cutting paths directly on the material,
Exactly. The geometry is mathematically locked in.
which completely removes the manual variables, the fatigue, the slight hand tremors, or even, the physical wear and tear of tracing a cardboard template 1,000 times. But reading through the Velocity Plotters breakdown, I actually had to stop and reevaluate my own assumptions here.
Oh, how so?
Well, if the end goal is the cut, does the precision just start when the blade hits the fabric?
If we connect this to the bigger picture, that is probably the most common misconception.
Right, because I just assumed you buy a fancy machine and boom, perfect cuts.
You would think the magic is entirely in the hardware of the cutting bed. But precision actually starts way before the cut ever happens. It requires evaluating the entire workflow, literally starting from the very first physical pattern.
Wow.
You cannot just buy an advanced digital cutter, plug it in, and expect flawless car seats if the geometric data you're feeding it is flawed from the start.
Which brings up a fascinating logistical nightmare, Resi, because a lot of these legacy operations still use physical templates.
Yeah, they do.
We're talking about literal pieces of heavy paper or plastic or cardboard just hanging on a factory wall somewhere, and they warp due to humidity. Their edges get worn down from being traced over and over, or they just get lost entirely.
Exactly.
So we have this digital DNA concept, but How do we get a physical, warped piece of cardboard into a flawless digital environment? The source points to Velocity's V-Shoot camera digitizing system.
Right, so moving from physical reality to digital optimization is the critical first hurdle.
Hmm.
The V-Shoot system uses a camera-based, non-contact capture method. So instead of someone manually measuring a pattern or tracing it on a digital tablet, which again introduces human error, this system visually photographs the physical patterns and turns them into reusable, editable digital files.
Okay, wait, I have to push back on that.
Go for it.
If they're just taking a photograph of a physical template laid out on a table, doesn't a camera lens inherently introduce optical distortion? I mean, especially around the edges of the frame.
Yeah, the fisheye effect.
Exactly. How is a photograph accurate to the sub-millimeter level required for, like, aerospace or automotive parts?
That is a great catch, and it's exactly why you can't just use a smartphone or a standard camera for this. The V-Shoot system uses highly specialized calibration software.
Oh, I see.
Yeah, it maps the specific optical distortion profile of that exact lens and neutralizes it mathematically. It basically flattens the image data, correcting for perspective and lens curvature to extract a true vector outline.
So it's not just saving a JPEG.
No, not at all. It's translating visual edges into precise geometric coordinates.
So it's effectively extracting the true mathematical intent of the pattern, regardless of minor physical wear on the cardboard.
Yes, exactly. And for automotive manufacturing, establishing that single source of truth is critical. A digital pattern library ensures everyone, engineering, production, everybody, is using the exact, approved, current version of a pattern.
No more digging around for the right piece of paper.
Right. It allows them to preserve existing patterns digitally forever, meaning they can perfectly reproduce a seat cover for a 10-year-old legacy vehicle without sifting through an archive of degrading cardboard.
Okay, so we have the digital DNA secured, the pattern is in the computer, but now we hit the next major problem in the workflow.
The material utilization.
Yes. You have this incredibly expensive, irregular hide of leather, or maybe a massive roll of technical fabric.
Dude.
How do you fit 50 complex puzzle pieces onto it without wasting half the material?
It's a huge challenge.
The source heavily emphasizes a software process called nesting within their Vetagraph CAD system. Wait, so is nesting basically just playing a high-stakes game of Tetris with car parts on a computer screen?
Yeah, it is. But the computational complexity goes way beyond what a human could do. Nesting is the mathematical process of arranging dozens of uniquely shaped components, curves, straight edges, weird, irregular cutouts, within the available surface area of the material.
Right.
The Vetagraph CAD software isn't just randomly dropping pieces into empty spaces. The algorithms are evaluating thousands of rotational permutations per second.
Because every square inch of that technical textile or premium leather that ends up on the cutting room floor is literally just profit going straight in the trash.
Precisely. And it's evaluating those layouts while respecting real-world manufacturing constraints.
What do you mean by constraints?
Well, for example, some fabrics have a stretch direction, right? Or leather has a specific grain. The nesting algorithm calculates the tightest possible bounding boxes for each part, while ensuring all pieces are oriented correctly relative to the material's grain.
Wow, okay.
It controls the buffer spacing between parts down to a fraction of a millimeter. Doing this optimization computationally on a screen is infinitely more cost-effective than discovering a geometric flaw after the material is already being sliced up.
That makes total sense. And the software lets engineers standardize dimensions and verify everything fits together before cutting. But this highlights a major communication bottleneck to me.
The translation phase.
Yeah. We have our perfectly nested digital file sitting in the CAD software. How does the computer safely hand that blueprint over to the actual cutting machinery without something getting lost in translation? I assume it's not like you just hit print, like sending a Word doc to an office printer.
No, it's quite a bit more complex. This dives into how manufacturing machinery actually interprets data. You can have a perfect design in your CAD software, which is usually defining geometry, right?
Right.
The software understands what a circle or a spline curve is. These are often saved as DXF or DWG files. But the actual cutting machine's hardware doesn't necessarily speak that language natively.
Wait, the cutting machine doesn't know what a circle is?
Not in the same way your computer does.
Mm-hmm.
The cutter operates on raw motor instructions. It needs equipment-ready formats, typically PLT or HPGL files.
Okay.
These files basically tell the stepper motors, move the blade X coordinates to the left and Y coordinates up at this specific speed. If the translation between the CAD geometry and the machine instructions isn't perfect, your perfectly smooth curve gets interpreted as a series of jagged, straight lines.
Oh, wow. The source notes that incompatible files can actually alter the pattern geometry during that handoff. Like, the machine might literally drop a crucial reference notch entirely just because the translator software didn't understand the CAD data.
That happens all the time with generic software, and that is why a dedicated translator is required. Velocity's workflow involves their easy plot software to handle this specific conversion.
So it acts as the bridge.
Exactly. It converts CAD files into the formats the cutting hardware requires while fiercely preserving the exact scale, the vector structure, and the correct line relationships. It ensures that the mathematical perfection you achieved in the nesting stage isn't degraded when it becomes physical motor instructions.
Okay, that makes perfect sense. The instructions are translated flawlessly. So now we finally get to the actual hardware, the Velocity ProCut X single ply cutter.
The main event.
Yes. And I have a major question here about the mechanics of this. So, what does this all mean?
Mhm.
And more importantly, why single ply?
Yeah.
I mean, if a car manufacturer wants to go fast and produce thousands of car seats, shouldn't they just stack 50 layers of vinyl and cut them all at once like a giant sandwich? Doesn't cutting one ply at a time severely throttle their output?
What's fascinating here is that speed in manufacturing is completely an illusion if it sacrifices tolerance. Single-ply technology is actually superior and deliberately chosen for the specific demands of automotive interiors.
Really?
Yeah, in like fast fashion apparel, you might see massive multi-ply cutters slicing through dozens of layers of cheap cotton. But automotive interiors deal with high-value, highly resistant materials. Premium leathers, heavy technical textiles, carbon fiber composites, thick foams.
Right. So what actually happens physically if you try to punch a vibrating blade through 4 inches of stacked foam or slippery vinyl?
You experience material shear and vertical blade deflection.
Oh, the blade bends.
Exactly. As the blade presses down and drags through the stack, the pressure causes the layers in the middle and the bottom to slide slightly out of alignment. Furthermore, the physical resistance of the material can cause the blade itself to bend slightly on a microscopic level.
Which means the piece on the very top of the stack is cut perfectly to the CAD file, but piece number 40 at the bottom is cut significantly smaller or wider.
Exactly. And when you're dealing with the complex geometries required to wrap a curved dashboard or a seat frame, you just cannot afford that dimensional variation. Processing one single layer at a time allows the ProCut X operator to maintain absolute control over the usable surface.
Okay, I see.
A vacuum system holds that single layer perfectly flat against the cutting bed, preventing the shifting and sliding that ruins stacked cuts. It guarantees that the 1,000th piece you cut is dimensionally identical to the very first one.
And I guess it seems uniquely suited for modern manufacturing trends anyway, right? Like short production runs, prototypes, custom on-demand orders, where you're only cutting one specific set of components rather than 10,000 identical pieces.
It is highly adaptable for that, yes. But there's another crucial reason single ply is preferred, especially when dealing with natural materials like leather. A perfect digital cut, the absolute best mathematical path a blade can take, is actually completely useless if you execute it right over a natural defect.
Right, of course. Cowhides have, scars, insect bites, stretch marks, plus specific grain directions. But the machine is blind to the physical realities of the leather on the bed. How does a digital system see the material to know where not to cut?
This is where we bridge the digital data and the physical reality. The ProCut X incorporates a system called ViewMatch. It's a visual projection system mounted right above the cutting bed.
So it's effectively overlaying a digital UI onto a raw piece of cowhide.
That is exactly the way to conceptualize it. It visually projects the precise glowing digital outlines of the nested parts directly onto the surface of the physical leather or textile.
Oh, wow.
This gives the human operator incredible power. If they see a visible defect in the leather, or if they need to carefully align a specific printed design or texture grain, they can literally look at the projected light, use the system to grab the digital file, and slide the projected pattern a few inches to avoid the scar.
They're adjusting the underlying code by looking directly at the physical material. They can literally see exactly where the blade will fall and make real-time millimeter adjustments before the blade drops.
Exactly. It treats a highly variable natural material with the precision of digital software. And it ensures that every single square inch of high-value material is used efficiently. You aren't accidentally putting a natural blemish right in the middle of a luxury steering wheel cover.
It brings human judgment back into the process without sacrificing the mechanical precision.
Precisely.
But the cutter isn't just cutting the outside silhouette of the seat cover, right? The source makes a huge point about automating operations beyond the outer contour cut.
Yeah, if you look closely at an automotive interior panel before it's sewn together, it is full of internal engineering details. It has internal holes for headrest posts. It has V-shaped notches along the edges to help the sewing team align two highly curved pieces perfectly. It has tiny reference marks and sewing guides.
And historically, someone was probably adding those in manually after the main cut, right? Maybe taking the cut piece, laying a plastic stencil over it, and hitting it with a specialized hole punch or a marker.
Which, again, introduces that human error we talked about at the beginning.
Right, because if a human manually punches an alignment notch even a millimeter off, the sewing team matches it up and suddenly the whole seam puckers.
Yes. The geometric relationship between the outer edge of the panel and those internal holes is absolutely critical. The digital system embeds all of these internal reference marks, perforations, and straight cuts directly into the same CAD file.
Oh, so it happens at the same time.
Exactly. The ProCut X executes them automatically according to predefined mathematical coordinates, all in the exact same pass as the outer contour cut.
I want to pause on this for you, the listener, because this is the real secret behind what we take for granted. The next time you see perfectly even stitching wrapping around a complex center console, it is specifically because these internal reference marks and alignment notches were digitally plotted by a machine to sub-millimeter accuracy. The sewing operator isn't guessing. They are just matching up perfectly generated digital coordinates.
It radically simplifies final assembly. The assembly team isn't fighting the material to make it fit. The material is engineered to fit perfectly from the moment it leaves the cutting bed.
So we have this incredibly automated, highly advanced workflow. But it brings up two big logistical questions for me. First, automotive design requires a massive amount of physical testing, right? How does a factory test a design physically before committing to a full production run on these fabric machines? And second, what happens to the human workers?
Let's address the prototyping and physical validation first. A mature development process requires processing rigid or semi-rigid materials, thick cardboard, PVC panels, or industrial plastics to build physical mock-ups or templates.
Right?
You need to verify the ergonomics and fitment physically before you scale up to cutting thousands of yards of expensive vinyl. For this, Velocity offers their flatbed plotter and cutter.
So this is like a specialized cousin to the ProCut X, but designed for different physics.
Exactly. It operates on a flat, stationary surface rather than a conveyor system, which is ideal for rigid materials. It allows engineers to validate the geometry of a design physically, run samples, and test the fitment.
Oh, I see.
If the PDC template fits the seat frame perfectly, they know the digital file is flawless, and they can send that exact same data to the ProCut X for the final fabric.
Okay, so if we pull back and look at the whole integrated workflow Velocity is outlining, it's a completely seamless journey. We capture the physical pattern and neutralize distortion with the V-shoot camera. We optimize that digital file and run nesting algorithms in Vetagraph CAD to save material. Then we translate the geometry into motor instructions using EasyPlot. We project the UI onto the physical material to check the grain with ViewMatch, and then execute the single ply cut on the ProCut X, including all internal notches, with absolute dimensional stability. Validate, inspect, boom.
And notice how the precision relies entirely on the data flowing seamlessly from one stage to the next.
Yeah.
The breakdown warns that precision plummets when stages operate independently. If the CAD software is outputting an incompatible file, or the operator cannot project the image to avoid a defect, the hardware speed doesn't matter. The whole ecosystem is designed to connect digitizing, preparation, and execution into one continuous digital thread.
Which brings me back to my second question. With all this automated calculation, what actually happens to the operator? I mean, we hear so much about automation replacing jobs, so we aren't removing the human from the factory floor. We're essentially upgrading them from a pair of manual scissors to a systems manager.
Yep. Exactly. Automation in this specific context evolves the operator's role. It does not replace them. The operator is no longer relied upon for brute manual precision or holding scissors at a perfect 90-degree angle for 8 straight hours.
Sounds exhausting.
It is. Instead, their expertise is elevated. They focus on file selection, material prep, configuring the machine's blade tools and pressure settings for different fabrics, utilizing the projection system to analyze the cowhide, and carrying out rigorous quality control.
Right. The human is making the high-level judgment calls like dealing with the variability of natural materials, while the machine handles the relentless mathematical execution.
Precisely. And the massive benefit here is consistency. In manual cutting, your precision varies based on the varying hand strength or experience level of whoever happens to be working the Tuesday morning shift versus the Friday night shift.
Oh, absolutely.
In a digital workflow, consistency is maintained across different operators because the digital file drives the precision, not the worker's hands.
So to summarize the core takeaways from this breakdown, implementing this level of digital cutting gives a manufacturer unmatched part repeatability. It minimizes manual dimensional errors to basically zero. It vastly accelerates how fast they can prototype new designs. And perhaps most importantly for their bottom line, it results in incredible material utilization.
Those are the direct mechanical benefits for sure,
Yeah.
but the source material also offers a very practical piece of advice for any facility looking to upgrade.
Yeah.
They advise against just looking at a catalog and buying a machine based on advertised cutting speed or price.
Because an operation building highly customized bespoke interiors for luxury sports cars has radically different physics and workflow needs than a factory pumping out 50,000 identical seats for a standard commuter sedan, right?
Exactly. The key takeaway is that an operation must perform a deep process analysis first. They need to evaluate their specific materials. Are they cutting dense foam, highly stretchable knits, or natural leather?
Right.
What are their maximum part sizes? What is their daily volume? What about floor space? What CAD formats is their design team currently using? Only by understanding those specific parameters can they pick the right mix of hardware and software. It is about building a tailored ecosystem, not just buying a faster blade.
It really is a complete paradigm shift from the old days of chalk marks and heavy scissors. And it leaves me with this final provocative thought for you to chew on.
Okay, let's hear it.
If this entire ecosystem of digital capture, advanced nesting algorithms, and single-ply execution is currently transforming the automotive interiors we sit in every day, driving down waste and driving up perfection, how long until this exact same ultra-precise, waste-reducing digital workflow completely reshapes how our custom clothing or even our living room furniture is manufactured on demand?
It's bound to happen.
Right. If a machine can perfectly map a cowhide to build a car seat, your next custom sofa might be engineered with the exact same aerospace-level precision.
The underlying algorithms and hardware are definitely adaptable. It's a fascinating trajectory to watch as other industries start to recognize the value of this standard of digital perfection.
Something to think about the next time you admire perfectly even stitching. Until next time.